Okay. So in this section, section 3.3, we're going to be talking more about functions and their graphs and property of functions. We're going to be talking about even and odd functions and how to determine whether they're even and odd. We're going to talk about determining increasing, decreasing, or constant intervals of a function. And we are going to talk about how to locate local maximum and local minimum, and also absolute maximum and absolute minimum, and how to use our calculator to find all of these as well. And then we're going to talk about that average rate of change of a function. Okay, so a lot of this should be a review, so I'm going to go over it pretty quickly because I don't want to make this video too long, and you can pause it and rewind it if you need to. So first of all, a function f is even if for every number x in its domain, the number negative x is also in its domain, and f of negative x is equal to f of x. So if I plug negative x in for x, then it should equal the same function, is what that says. And if that is the case, then it would be even. And this is a graph of an even function. A function is even if it's symmetric with respect to the y-axis. So that's the y-axis, and you can see that there is symmetry on the left and the right of the y-axis. So that's another way we can tell whether a function is even. And then whenever it says for every number x in its domain, the number negative x. So if you look at these points down here, the one on the left would be negative x, and then f of negative x, and the one on the right would just be x, positive x, and then f of x. They would have the same y value right there, but the x value would just be negative versions of each other. And then a function is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x is equal to negative f of x, which means if we plug in negative x to the function and then we get the same function but everything is opposite signs, then we know that that function is odd. And an odd function is symmetric with respect to the origin. We're going to talk more about that symmetry, but it should be kind of a review. But this is an example of a graph that is odd, and it is symmetric about the origin. So this is just saying what I said. If it's even, it's symmetric with respect to the y-axis, and if it's odd, then it is symmetric with respect to the origin. So let's talk about how we can determine whether a function is even, odd, or neither by looking at a graph. So in this first example, this graph is not symmetric about the y-axis. No symmetry. If I cut that down, the left side is totally different from the right side. And this would be the left, and this would be the right side of that y-axis. So they're not the same, so it's not symmetric. And then it's also not symmetric about the origin. So this function is neither even or odd. Next example, B, we see that this function is symmetric about the y-axis, because if I fold the left piece of that function over the y-axis, it would coincide with the right side. So this function is even because it is symmetric with respect to the y-axis. And then the other example, C, this function is symmetric with respect to the origin. You can kind of visually tell, like if I pick a point here and then I try to pick a point here across from the origin, then this x value, let's call it x1, would be the x value of that point, and then the y value would be f of x1. And the one over here would be negative x1, and negative f of x1. So same values, just negative of each other. So it's like a mirror image if I folded it over the origin on top of itself. I'm sorry, I said that wrong. It's actually, if you rotate it 180 degrees, then it'll line up on itself. So that one is symmetric with respect to the origin. Okay, so now we're going to look at a couple different functions and determine whether they're even, odd, or neither using a graphing calculator, and then I'm going to show you how to do it algebraically. So the first example is f of x is equal to 2x squared plus 3. So if you graph this on your graphing calculator, you'll get the graph to the right, and it's pretty easy to see that this is symmetric with respect to the y-axis. So this function is even. And algebraically, if we didn't have a graph and we wanted to see if it was even, then I would plug in negative x to my function. So everywhere I see an x, and negative x squared is positive x squared, so that would be 2x squared plus 3. And this is exactly the same as what we started with. So because I got the same function f of x, that also tells me that this is even, and it's symmetric about the y-axis. Next example is g of x is equal to x cubed plus 3. So if we look at the graph to the right, I don't see any symmetry. So there's no symmetry with respect to the y-axis or the origin. So this function is neither even or odd, nor odd. But if we did it algebraically, I would plug negative x into my function again, and that would give me negative x cubed plus 3. Negative x cubed is negative x cubed plus 3. And this is not the function that we started with, and it's also not the negative version, because if I multiply this function by negative up here, let me use this would be negative x cubed minus 3. So it's not the opposite signs because that 3 is still positive. So this is neither even nor odd. Next example is x cubed plus 4x. So if we graph that, we can see that it's not symmetric about the y-axis, but it is symmetric about the origin, because again, if I picked a point here, it would coincide with a point in that third quadrant. But to test this algebraically, we can plug negative x into h. So we would be replacing all the x's with negative x. Negative x cubed is still negative x cubed, and 4 times negative x is negative 4x. So this is the opposite sign of our original h of x. So this is equal to negative times h of x, which again tells us that this is odd, and that it's symmetric with respect to the origin. All right. So let's talk about how we can tell whether a function is increasing, decreasing, or constant, and which intervals is the function increasing, decreasing, or constant. So a function is increasing on an interval I if for any choice of x1 and x2 in I, so any values of x in that interval, where x1 is less than x2, then the outputs of those, so f of x1, will also be less than f of x2. And I'm going to show you a picture of a graph on the other side that really makes this make more sense. And then a function is decreasing on an interval I if for any choice of values of x where x1 is less than x2, then the output of x1 will be greater than the output of x2. And then of course a function is constant on an interval I if for all choice of x and I the values of f of x are equal. So they have the same y value. Okay, so I'm going to zoom in a little bit just to kind of help make this make sense. So if I have this graph and I have x1 here and x2 here, then x1 would obviously be less than x2. And if I inspected their points on the graph to be here and here, then that output would be f of x1, and that would be less than the output of f of x2. So if the first x value comes before x2 and it is less than the y value of x2, then that function is increasing. Now visually, we can see this if we look at it from left to right. The blue function is increasing. If I start from the left and I put a stick figure little guy on this curve and I told him to walk to the right, he'd have to walk uphill. So he's going upwards, so it's increasing. For decreasing, if x1 is less than x2, then the output for x1 should be greater than the output for x2. So it's getting smaller. And if I put a little guy from left to right on this curve and told him to walk to the right, he'd be walking downhill. So it's decreasing. And then constant just means it's constant. It's not changing. So my little stick guy is just walking horizontally. Okay. So if we're given a graph and we're asked to determine the values of x for which the function is increasing, decreasing, or constant, then it's asking for the intervals of the x values for which it is increasing, decreasing, or constant. Let me see the next. Okay, so that's what this slide says. We are looking for the intervals involving the independent variable x for which it is increasing or decreasing or constant. So let's start with constant. My iPad's doing okay. So the intervals for which the function is constant is going to be from -4 to -2. That piece of my graph is going in a straight horizontal line. So that interval would start at -4 and go to -2. And then increasing would be from -2 to 0. And I'm so sorry, this should be parentheses, not brackets. Anytime we're talking about increasing, decreasing, or constant, we're just talking about parentheses here because the endpoints are not necessarily increasing or decreasing or constant. They're just there. So for increasing, this would be from -2 to 0, the x value of 0. But then we have another one. So from here, x equals 3 to x equals 4. Now on these, usually they'll just tell you to write the intervals in commas. So this would be comma and then the interval from 3 to 4. Parentheses. And then for decreasing, the intervals for which it's decreasing would be from 0 to 3. And that would be it. Okay. So the next thing we're going to talk about with functions is the local maximum and local minimum values. So if we look at this picture, the picture on the left is an example of a local maximum. And this is because the point here is the largest y value in that closed interval. And so local maximums occur when we have those like peaks of the hills. Like this is like an entire hill. So at that peak of the hill is where we would have a local maximum. And then the local minimum is like the dip in the hill. And that's the smallest y value in that neighborhood of the point. So local means in the neighborhood. But I'm going to give you a more precise meaning in the next slide. So a function f has a local maximum at c, this would be the x value, if there's an open interval I containing c such that the output of c is greater than all outputs for the x in the interval. And this value of the output of c is called the local maximum value of f. And then a function f has a local minimum at c if there's an open interval I containing c such that the output is less than or equal to all the other outputs for x in that interval. And that's called a local minimum value of f. Okay. So for example, this slide gives us a picture of a graph, and it's going to ask us at what x values, if any, does f have a local maximum, and then it wants us to list the local maximum values. So when it's talking about in the interval, we're talking about the inside of the endpoints. This one doesn't even really have an endpoint because this is going forever. So I'm just talking about the dips and the peaks of the hill in between the ends of my function. So the first local maximum I see is this point here. That is a peak of a hill within that function. So locally, it's a maximum value. And it says what number x, if any, does f have a local maximum? That would be the x value of 0. Oops, sorry. And then it says to list the local maximum value, that's going to be talking about the y value. So the actual local maximum value is the y value, and that value is 3. Oh, I'm so sorry. This is x equals 0. The value of x there is 0, not 3. The y value is 3. My bad. Okay, the next one. At what numbers of x, if any, does f have a local minimum? So the local minimum is going to be the bottom of any peaks. So that would be these two. And the values of x that occurs at is -2 and 1. And the actual local minimum values, which is the y values, is -1 and 0. And then C, it says to find the intervals of which f is increasing and the intervals on which it is decreasing. And let me actually use different colors. I'll use red for increasing. So our function is increasing from here to here, and then here off to infinity. So for increasing intervals, first one would start at -2 and stop at 0. And then that second one starts at x is 1 and goes off to infinity. And then decreasing would be from here to here, and then from here to here. So that first interval keeps going in the negative x direction, so that would be from -infinity to -2, and then from 0 to 1. All right, so those were local maximum and minimums. And now we are going to talk about the absolute maximum and the absolute minimum. So if we let f be a function defined on some interval I, and if there is a number u in I for which the output of u is greater than or equal to all outputs for all the x in I, then f has an absolute maximum at u. And the output would be the absolute maximum value of f on I. So the difference here between the absolute and the local is that our interval I is going to include all the values of our function. So we're not just looking in a neighborhood of an interval of x values, we're looking at all the x values in our domain. So an absolute maximum is going to be the absolute largest value of our function. And then for the absolute minimum, if there is a x value in I, say v, then the output of v will be less than or equal to all the outputs for all the x in I. And this would be an absolute minimum. Okay, so this is a very general function here. And if you notice the endpoints are ending, they're not going forever because we don't have an arrow coming out of them. So the domain of this function is actually just from A to B. And if we look at this x value of u here, the output, f of u, is the largest value in this entire function, the largest y value. So that is going to be our absolute maximum because of that. And then f of v, which is right here. This is the smallest output, or the smallest y value of our function, and it's smaller than all the other outputs in this entire function. So therefore, that is an absolute minimum. So these values are also sometimes called absolute extrema, or extreme values of f on I. Okay, so let's do a couple of these examples. So this one is giving us a picture of a graph, and they want us to identify any absolute maximum or absolute minimum if they exist. And then they also want us to find any local maxima or local minima. So first of all, let's just talk about the domain in general of this function. So it is starting at the x value of 0, and it ends at the x value of 5. And these are included because they have closed dots, so that's our domain of the function. The absolute maximum, is going to be the value 6, because that's the y value of the largest, that is the largest y value of this entire function. So that actual absolute maximum value is equal to 6, and it occurs at the x value of 3. And the absolute minimum will be the smallest value of this function, and that's going to be, let me highlight this, that's going to be right here, which is 2. That's the smallest y value of our function. Okay, and then local maxima. This is going to be any of the peaks in the middle of my endpoints. So this would be 1, and that value would be 6 as well. And then the local minima will be any of the dips. Let me use some color here. Okay, and so that one is going to be this point right, no, I'm sorry. Yes, it'll be that point right there. Because if we're looking in the neighborhood of the point, that is one of our dips. So local minima, this value would be equal to 3. So for the absolute and maximum, these can be endpoints, as we just seen with the absolute minimum, because this is an endpoint of our function. But these cannot be. Can't be endpoints. They have to be inside, in between the endpoints for it to be a local max or a local min. Okay, next example. First, let's talk about the domain of this example. Notice that this example has an open hole at that point 2, 6. So that x value of 2 is not included. So it actually starts at 1 and goes to 2 with a parentheses. And then we have to start back at 2 and go to 4. So the 2 is not included. So let's talk about the absolute max. So because this point has a hole in it, I can't include that as a maximum, and there is no other maximum value within this function. So this one would have none. Absolute minimum would be equal to this y value, should be 3. Because that's the smallest y value in our entire function. And then there would be no local minima or maxima. because there's nothing happening locally, and that 0.2 comma 6 is an open hole, so I can't include that in the maxima. Okay, the next one, let's talk about the domain. So this one also has a hole on this point right here. So I can start at that x value of 1, but it'll be a parentheses. And it goes on until 6, the bracket. That looks crazy. So the absolute maximum will be equal to this y value of 3. The absolute minimum is actually going to be equal to 1. So that's the smallest y value on my function. And the local minimum value is also equal to 1. Now this function has a local minimum on the interval of 2, 4. So the actual local minimum is equal to 1, but it occurs on the x values from 2 to 4. And then there will be no local maxima. Okay, I think I'm going to skip these. You can look at them on your own. They have a couple of other examples on there of that. Okay, so the extreme value theorem says that if a function f is continuous on a closed interval from a to b, then f has an absolute maximum and an absolute minimum on that interval. So let's look at a couple examples on a graphing utility. So we are given this function, f of x is equal to negative 2x cubed plus 5x squared plus 1. And we are only interested on looking at this graph for the interval of x values from negative 3 to 3. And they want us to approximate where this function has a local maximum and where it has a local minimum. And then it wants us to determine where f is increasing and decreasing. So if I go to my graphing calculator, take a picture of this real quick. And I type in this function, negative 2x cubed plus 5x squared plus 1. And then I graph it. And I need to fix my window. And they told me to only graph it for the values of x from negative 3 to 3. And leave that like that. I'll make this be negative 10 to 10 by scale of 1. Okay, so it looks like this. So again, we're trying to find the local maximum and the local minimum. This function will not have an absolute maximum or min because the end points are going on forever. But to find these local max and min, you can hit second, trace, and then click on minimum. And this first dip here is going to be a local min. So we're going to move that little cursor a little bit to the left of it, hit enter, and then a little bit to the right, hit enter again. And it tells us that that y value is equal to 1. Let me see. Okay, and that's what they get here. So we find that that local minimum value is equal to 1 because that's the y value. And this x value is very close to 0. That e to the negative 6 is the same thing as, rewrite this as saying times 10 to the negative 6 power. This is scientific notation. So that tells me to move this decimal over 6 times. And so this would be very, very close to 0. So if you ever get something like that, then you can just round it off to 0. Okay, going back, now we're going to try and find the local max. So we go second, calculate again, go down to maximum, move that little cursor to the left of where you think that maximum value is, and then to the right, enter again, and this y value is 5.62962, blah, blah, blah. And it occurs at the x value of 1.6666685. So let's see. It's exactly what they got. So now they're just rounding this, which in your homework it'll tell you if they want you to round your answer. And the y value, which is the local maximum, is that 5.63. So that's a way you can use your calculator to find those. And then I'm going to draw. So we found that this point here was 0, 1. And then we found this point to be 1.67, 5.63. So after we find those, then we can use those to determine our intervals of increasing and decreasing. So the function is decreasing from here to here, and then from here to here. So decreasing, they get that is from hold on, I don't know what they, okay. Oh, that's right. Okay. So remember, they told us to cut off our domain for x. So they told us to cut our domain to this. Let me make sure. Yeah. So because they told us to cut off our domain right here, this x value is equal to -3, and this value is equal to 3. So they just want me to include the intervals of these values. So the first decreasing would be from -3 up until the x value of 0. That's where they get that from. And then from 1.67 to 3. And then for increasing, it will be increasing from here to here. And that interval would be from 0 to 1.67. Okay. So finally, we're going to talk about this average rate of change formula. And remember, we already kind of talked about a very similar formula, which was the difference quotient. And I told you that that was the same thing as the average rate of change. So this is really the same formula, just kind of written differently. So if we have a function on an interval from a to b, well, really the interval can be bigger than a to b, but say we had a here and b here. And then we had this function. Then this point would be a comma f of a. And this point would be b comma f of b, which I think they have this drawing on the next slide. But so again, the slope formula, if you remember, it's y2 minus y1 over x2 minus x1. Well, our x2 would be b, and our x1 would be a. And then our y2 would be f of b, and our y1 would be f of a. So it's the same thing as finding the slope, but now we're just kind of finding the slope of the secant line that crosses through these 2 points. And we're going to talk about that as well. Okay, so let's look at an example. It says find the average rate of change of the function f of x is equal to x squared plus 1. And they want me to find the average rate of change from the x values 0 to 1, and then 1 to 2 and 0 to 2. So let's look at 0 to 1 first. So to find the average rate of change of this function from 0 to 1, we're going to plug this into the formula. So 0 would be my x1, and 1 would be my x2, or I guess in this case, my a to b. And so just to remind you of that formula, it's going to be f of b minus f of a over b minus a. So f of b would be f of 1, f of 0, or f of a would be f of 0. And let me use a different color. So f of 1, which is the value of y when x is 1, is going to be equal to 2 because of that. And f of 0 is going to be equal to 1. So plugging that in, we get 2 minus 1 over 1 minus 0. 2 minus 1 is 1, 1 minus 0 is 1, so this is just equal to 1. So the average rate of change of that function from the x value 0 to 1 is equal to 1. Another example. Same function, but now we are finding the average rate of change from 1 to 2. So 1 will be our a, 2 will be our b. So f of b will be equal to f of 2. And if I look on x is 2 and find the y value, that would be 5. And f of 1, if I find the x value of 1, that would be equal to 2. So this would be 5 minus 2 over 2 minus 1, which is 3 over 1, which is 3. Okay, I think I'm going to skip that example. Okay, so here is a picture of that, kind of like that graph that I was showing you. And we have our x values from A to B, and then their corresponding points. And if we connect those two dots using a line, this would be called the secant line. So secant line just means a line that crosses a function at 2 points. So when we're finding the average rate of change of a function from A to B, we're really finding the slope of the secant line containing those 2 points. Okay, this is my last example, so we're almost done. So this says, suppose that g of x is equal to x squared minus 3x plus 2. And it wants us to find the average rate of change of g from 1 to 3. And then it wants us to find an equation of the secant line containing 1 comma g of 1 and 3 comma g of 3. And I'll talk about c in a second. So first, let's find the average rate of change. So again, when it says from 1 to 3, 1 will be our A, 3 will be our B. So the interval will be from 1 to 3. And that formula for the average rate of change is f of b minus f of a over b minus a. So b is 3. And a is 1. And so f of b would be g of 3. Because in this case our function is called g, so just don't let that f confuse you. But g of 3 minus g of 1. So we need to find g of 3. So g of 3 is equal to 3 squared minus 3 times 3 plus 2. 3 squared is 9. Negative 3 times 3 is negative 9. So this just equals 2. So g of 3 is equal to 2. And g of 1 is equal to 1 squared minus 3 times 1 plus 2. Should be 1 minus 3 plus 2, which would be negative 2 plus 2, which is 0. So g of 1 is equal to 0. So this would become 2 minus 0 over 3 minus 1, which would be 2 over 2, which would be 1. So we just found the slope of the secant line that passes through these 2 points. And we found the average rate of change of this function from 1 to 3. So now let's find the equation of the secant line. So remember, we just found g of 3 to be 2 and g of 1 to be 0. So we really just found 2 points. We found 3 comma 2 on our graph, and we found 1 comma 0 on our graph. And these are the 2 points that our secant line goes through. Okay? So we just found the slope of the line that goes through these 2 points. So if I have a slope, which I know is equal to 1 because of what I just did on the previous slide, and then I have these 2 points, then I can create an equation of this line. I'm going to choose one of these points, and I'll choose 1 comma 0 because it's easier to work with. So plugging it into the point slope form, and this notation is just saying the slope of the secant line, which is 1, and the y1, x1 will be the point on this line. So this would be y minus 0 equals to 1 times x minus 1.
which would just give us y is equal to x minus 1. And that would be the equation of the secant line that passes through those 2 points. So to bring this all together, this is a picture of the graph. The blue is the picture of our original function we started with. And then we picked 2 points, which they gave us the points. First one, the x value they gave us was 1. And then the second one, the x value they gave us was 3. So the red line is the secant line that goes through those 2 points. And what we did is we found the slope of that line, and we found that slope to be 1. And then we chose one of those points and created the equation of that secant line, which gave us this equation. Okay, so that's the end of 3.3. So hopefully you have enough time to get caught up, and I will see you guys tomorrow.